Is that clear? How we arrive at the Hamiltonian?
Yes, sir.
Okay, so this is, so now that we have the Hamiltonian, we can write down very easily the Schrodinger equation. However, there is one thing, one subtlety in the Schrodinger equation. P is going to be replaced by minus I h bar gradient operator, right? So now the thing is that A itself is a function of space and maybe even time. So therefore, this thing and this thing, they are not going to commute. So classically, when we have a quantity like this, say P plus A squared, we can express this P squared plus A squared plus 2PA, right? But quantum mechanically, because one of them, there can be operators, we have to interpret it in a more mindful way. So quantum mechanically, this is going to be P squared plus A squared plus, say, PA plus AP, okay, with the minus sign and these things, all the bells and whistles, okay? So in quantum mechanics, we are going to write P minus Q by C of A as P squared minus Q by C bracket P dot A plus A dot P plus Q squared C squared A squared, okay? Mind you that both this guy, they're all operators. So if there's a wave function on the right, they're going to act on them. Okay? Any questions? I mean, this is just algebra.
No question, sir.
Okay, now what about gauge transformation? So under gauge transformation, the Hamiltonian this thing is going to change to P minus Q by C minus Q by C. So there's an A here, gradient of lambda plus Q phi, right? No, I think the Q phi was already there, yeah. Okay, so this is under gauge transformation in which phi goes to phi, so I'm not changing this here, okay? I'm doing a special gauge transformation. So I'm taking lambda to be time independent. So the time derivative is 0. So A goes to A plus grad of lambda, okay? So if I do this, is time independent. I mean, I can do that general thing, but it's not relevant for the discussion that we're going to have. So we see that under a gauge transformation, the Hamiltonian is not invariant. And, the gauge transformation is just, it's just rewriting the problem in different variables, right? In a different, slightly different variable. So the physics should not depend on the gauge transformation. So we are going to make some requirements that expectation values of operators will be invariant under gauge transformation. So suppose that we have the position operator. So we see that the position operator should not change under the gauge transformation, right? Because it doesn't have any P in it. So, so these are kind of, if you like, conjectures. So we want this to be, but under gauge transformation, the state may change to something like this. So we want, so under gauge transformation, alpha goes to alpha tilde, but P X remains the same. Okay, so this is something that we impose. Similarly, under the gauge transformation, the kinematical momentum, which is P minus EA by C, that should also not change. But we know that P does change, and this whole thing, changes to P minus EA A tilde. A tilde is the new. Sorry, I was wrong to say that P changes. What changes is A, right? Sorry. So because the kinematical momentum is the physical momentum, we impose these as our condition that needs to be satisfied, because these are the things that we are going to be able to measure physically. Okay, so these are requirements, physical requirements. So what we are saying is that under a gauge transformation, the state changes itself by some linear transformation, which we are calling G. So under a gauge transformation, alpha goes to alpha tilde by. Now, this requirement tells us that if I start with the right-hand side, the right-hand side is alpha tilde x hat alpha tilde, then this is going to be G alpha x hat G dagger alpha. So if this is going to be equal to alpha x of alpha, now alpha is arbitrary, then for this to be true, we have to have x equal to G dagger x hat of G, okay? So we want to find out what G is. So this is one property that G has to satisfy. Now what about the other one? The other one gives me, similarly, G dagger P minus Q by C A, but A changes by minus Q by C gradient of lambda G, and that has to be equal to P minus Q by C A. Okay, so this one comes from this equation. Okay, the right-hand side gives you this, and this is the left-hand side. Okay, now we can show that if G is given by the exponential of I Q lambda, lambda being this function, which is a function of x, divided by h bar c, then G dagger P G is going to be, now remember what is P? P is minus I h bar gradient, right? So there's going to be a G dagger here, and here we have minus I h bar gradient, and that is going to be acting on e to the power I q lambda by hc. So then we are going to have G inverse, but this thing acting on this is going to give me this factor times something, that derivative operator acting on this, right? So I'm going to get a factor of G here anyway. And then I have minus I H bar from here. And from the exponent, I'm going to get I Q by H dagger H bar C gradient of lambda. But here, H is going to cancel H. I squared is going to give me plus sign here. And as a result, I'm going to get, and this is going to be 1. So as a result, I'm going to get Q over C gradient of lambda. Okay? Right. So, but you see that P is an operator, right? So P is an operator. That means we have to add here P. So, okay, let me just recapitulate. This is what we want to, but this guy is acting on some wave function psi, right? So first, this is going to act on this thing, and that's going to give me this. It's going to give me QC gradient of this lambda times psi. But the second term is going to give me P acting on psi, right? So I can write that G dagger P G is equal to Q by C gradient of lambda plus P. Okay, is that clear? Is it clear where this P is coming from?
Yes, sir.
Yeah, because it's an operator, right? So it's gonna, by the Leibniz rule, it's going to keep acting on stuff. Okay, and now if I look at this expression, it's because X is just, the X operator in the position representation is nothing but just the number X. So this is going to be trivially true. Okay.